Hi, this is Professor Merrill-Lichty. In this video, I'm going to demonstrate the results given by the central limit theorem. The central limit theorem is one of the most important theorems known to man, and it justifies how much attention we pay in this class to the normal distribution. We're going to do this demonstration by simulating a series of dice rolls. If you think about rolling a six-sided die, all we're doing is selecting one of the numbers between 1 and 6. And if you guys were all here, I could just pass out some dice and have everybody roll and write down what the results are. But since you're not here, let's use Minitab to do this. So if we come over here to Calc and then Random Data, Integer, we can look at, we'll say C1. We're going to take 60 rolls of a six-sided die. So the minimum value is 1, the maximum value is 6, and we're going to put those in column number 1. So here we have the rolls of those die, and you can scroll down and see what these are. So let's look at a histogram. What do you expect this to look like? Graph, histogram. Just do the simple default, and let's change it to C1 and say OK. And here's our histogram, and maybe you were expecting something like this, maybe not, but it looks like 2 and 4 are happening quite a bit less than what we would expect. We would expect all of these to have 10 outcomes, and so the difference you see here is due to random variation, and it's difficult sometimes to see what the shape of the distribution is with a small number of observations. So let's do this again with Calc, Random Data, Integer, let's call it C2, and instead of 60, let's do 6,000 observations. So here we have C2. I won't scroll down on that, but let's look at a histogram for that as well. Change that to C2 and say OK. And this looks a lot more like what we would expect to see, a uniform distribution. So the central limit theorem is something that we can look at now because we've taken samples from a uniform distribution, and in fact let's do that again. There we go, Random Data, Integer, and we're going to do this now in columns C4 and C5, and we're going to do it 6,000 times, and you can see these two columns. But what we're really interested in here is not the histogram of each of these, but we want to look at the mean. So we'll say mean of 2 rolls. And so I hope you're paying attention how to do this stuff. We're going to go up here to Calc, and then row statistics, and we're going to pick the mean. And the columns that we want to put into this are going to be C4 through C5. And we want to store this in C6. You can see the remnants of the rest of the stuff in this data set. And we say OK. And so now let's look at the histogram of the mean of 2 rolls. And we get this thing. So this looks like a triangular distribution, and in fact it is triangular, but you can see that the shape of this thing is not anywhere near what a uniform random variable would look like. Okay, so the central limit theorem basically says the more samples that you have that go into each of these means, the more this distribution is going to look like a normal distribution. So here I've got 2 rolls and you can see over here I've got 5 roles. So same sort of deal as what we had. I created these earlier. Now I want to look at the histogram for the mean of 5 roles. So I'm going to go to Graph, Histogram, Simple, and now I want the mean of 5 roles. Say OK. And you can start to see this is starting to look like more like a normal distribution. So here's the triangular, here's 5 roles, and guess what else I've got here? You can't see it yet. Let me scroll over. Got 10 roles. So here's 10 roles. So let's look at the mean of 10 roles. Histogram, mean of 10 roles. Okay. And so this is now looking more and more like a normal distribution, which is, of course, what we get with the central limit theorem. Okay, so this comes from uniform data. What happens if we use something that's skewed? So I've got 30 columns of exponential random variables, random draws from exponential random variable, and this is a random variable that's sometimes used to model the life of some components, computer or hardware or mechanical or whatever. And so if we look at the histogram of that, and we'll just look at one of these columns just to see what, doesn't matter which one we look at. We see the lifetime of this random variable or the product that we're making, and it's very much skewed, very heavily skewed in the positive direction. So we've got 30 columns of this, and so what's going to happen when we take the average or the mean of these things? Well, let's come over here and look at the graph. Here's our distribution for the average of 30 exponential draws. So you can see this is starting to look like a normal distribution. And in fact, we could, because we have 30 observations, it doesn't matter what distribution is that we're sampling from, we can use this, use the normal random variable to approximate this. And so we've shown that the shape of the distribution converges to the normal distribution, but there is more to the central limit theorem. And that can be seen in looking at the mean and the standard deviation of the distribution of x bar. So the mean of x bar is mu, and the standard deviation of x bar is sigma divided by the square root of n. So let's look at the means and standard deviations and figure out what it is that is going on here. And let's come over here to Excel to examine this. So if we have a sample of size 1, 2, 5, or 10, then the theoretical mean should just be equal to 3.5. So if you take the numbers 1 through 6, add those up, you get 21. Divide that by 6, and that gives you 3.5. So this mean is going to be 3.5. The theoretical value for the standard deviation, on the other hand, comes from the formula in the textbook. I think it's in chapter 5. It might be equation 5.2 or 5.3. In any case, you can calculate this by taking the formula, the square root of the quantity b minus a, where b is 6 and a is 1. So the maximum value minus the minimum value plus 1, that squared minus 1, and then that whole quantity divided by 12, although the 12 needs to be inside of parentheses, inside the square root, so let's put in another parenthesis, and you can see where that number comes from. So this is sigma, and to get sigma for x bar, we just need to take this number and divide it by the square root of n. So if we come over here and take this number and divide it by the square root of n, which is that number, you see that we get something very similar, and the problem is that these are not the same, so let's just paste that in right here, and now you see these things are the same. So let's go back over to Minitab and see what the results are from our simulation and compare these. What we're going to do is go statistics, basic statistics, display descriptive statistics, and the variables that I want are C2, that's going to be just a single observation, so n is equal to 1. I want mean of 2 rows, mean of 5 rows, and mean of 10 rows. And the statistics that I want are just the mean, standard deviation. Get rid of all these other things, just because there's going to be a lot of clutter otherwise. And we'll say OK, and we'll say OK. And so here we have the mean and the standard deviation. For each of these things, it looks like I picked up the number of missing values, which I don't have. So to 2 decimal places, let's put this back over here into Excel. So we've got 3.50, 3.53, 3.53, 3.51, and 3.51. Okay, so that's the mean for each of these things, and it looks like they're pretty close to the theoretical values. Let's go over here now and look at the empirical standard deviation. So we have 1.69, 1.69, and it actually would round to 1.7, 1.23, change that, 1.70, 1.23, so we have 0.778, so 0.78, and 0.54. So we can see then that these things are matching up, and it turns out the bigger our sample size, the closer these things should be to each other. And but this is basically what's going on with the central limit theorem. The bigger your sample size, the closer you have something to the normal distribution. We saw the shapes of these things, and this is something that's a really important result that forms the basis of modern statistical analysis. So that's all I've got for this video.